The other day I came across some data about data engineers versus data scientists. And some information is from this article. Was pulled from looking at LinkedIn information. And so I looked at various positions, how many people on LinkedIn claim to have that skill, how many positions are advertised for that position. And so a big data engineer, there are almost 2,000 open positions, and about 4,000 people that claim to be a data engineer. A big data engineer, for a data engineer, it's like 16K open positions, so it's much bigger. But then there were like 40,000 people on LinkedIn that claim to be a data engineer. But the candidates per position is about the same, right? Data scientists, right? 20,000 open positions, but then there's almost 100,000 people on LinkedIn claim to be a data scientist. So the candidates per position is significantly higher. Web developer, 27,000 positions, but almost 300,000 people claiming to be a web developer. So that doesn't look very good, right? And then there's a marketing manager. Doesn't look. You better be a pretty good marketing manager to stick out in that crowd. Now, of course, we can always ask, how accurate is the data in terms of how likely it is of these positions to be advertised in LinkedIn, and how likely it is that people who claim to be have these skills actually do have those skills, right? I suspect a lot of people claim to be a web developer who are probably not ready to be a professional web developer at the current level, right? But it's less likely that someone's going to claim to be a data engineer and not have those skills, because those skills take some time to accumulate, and it's fairly easy to filter the ones out that don't know what they're talking about. Just some interesting information about job markets. So the article talked about, data scientists gets all the hype, but data engineers are also needed, and there's probably less competition for those jobs. And so I forgot where we left off last time, and the video recording there's some technical difficulties, so the application crashed in the middle of the class. I didn't notice. So, let's look at linear regression and just some fake random data, right? And yeah, correlation coefficient is pretty high, so it's, as you expect, that's pretty linear, particularly since it's coming from a particular linear, right, process where I just add a little random noise. And then Scikit Learn, the process is pretty similar to almost every model you want to build. First of all, we need to produce a independent variables, and I expect the independent variables to be in a two-dimensional array, and so I add an extra axis to the data. And then we create the model instance, and then we fit it to a given data. And this is pretty much, doesn't matter what you're doing, it's a pretty standard process. And you start looking at information about the model. It says the coefficient is 1.97, which is pretty good because I started out with the equation was 2 times x, so the coefficient is pretty close. Intercept is -9, and I was subtracting off 1, so again pretty close. And so we get this as a regression line that and so I just create a function to generate the regression line, and then we can actually we can plot it, and so we can actually plot the regression line. And there is a plot function will do it for us, but then we have no idea what the regression line is itself. And so the regression line is pretty easy to compute, but other models are slightly more complicated, so we can actually use a model to do a prediction for us. So again, I just generated sequence of points evenly spaced between -1 and 11. I then have to convert it to a 2D, and then I can call predict on the model to get the y value. And I can then plot and get the.
What exactly the 2D independent variable looks like? Is that kind of like a matrix? Every row is the independent variable, or every column is independent?
Yes, in this case, we only got one column, right? And so what this is going to do for us is going to create each row is going to be itself an array of one independent variable. Yeah, so and each row is a different value for. Oh, because what we're doing here, right, is this NP is basically a set of points from -1 to 11 space, but with 50 even space, right? So X is a vector of 50 elements. That's just how to add a new axis without adding any data to it. And he's looking it up now. And what did you find out? Yeah, it just adds another axis, right? And it's one of those things where we can do these weird things, and so we're creating this little language that we can put inside the angle brackets. You know, here we're just adding another dimension. We can also put two column labels, right? And it will select all the columns in between. So Scikit-Learn does it, but then it becomes hard to. Presumably it's the same regression line. This is where we can spend the entire course learning, just doing machine learning, because there's different types of regression, right? Linear regression is the simplest, but there's different ways to compute the regression. And then there's just all kinds of different ways. And the important thing here is overfitting. So if you remember from your math classes, if I've got n data points, I can always fit a polynomial curve to those data points exactly by using n plus 1 degrees, right? Or polynomial. So I can always fit those points exactly, right? That doesn't mean that function accurately reflects the underlying process, right? You know, so clearly this is a pretty linear. We've got a couple outliers, and you know we can fit it exactly, but what's going to happen now is this is just going to completely just plunge, and we're also going down, whereas the data is increasing, right? And so the problem is if you have enough levers to pull, you can always make your model more and more accurate to fit the particular piece of data you're looking at. That doesn't mean the model is going to be more accurate modeling the underlying process, right? And that's why, in general, what we do is when you've got a large data set, you're going to break it into several pieces. One piece is going to be a training set, right? And then we're going to use another set for validation, right? How well does it fit this data? That's a sample from the same populations we have. You know, how do we know that it's the right model to use? Well, there are a couple things we can do. One, we can look at the residuals. Residuals are just, you take that regression line and you then find how far each data point is from it, and then it should be, overall, you expect that difference to be about 0, and you expect similar number to be above and below. Right, and so we can take our actual values and subtract out the predicted values, and you know, right? The sum should be about 0, the mean should be about 0, and there are a few more values which are slightly more negative than positive values, but it doesn't seem too bad. We can also look at the coefficient determination. Again, we can spend, take a stat class and derive this formula. This is why it's important and why it does what it does. But most libraries now compute it for us. And we compute it, and it explains how much variance, right? The model explains the data, and here it's 0.97 plus, so it's explaining nearly all the variance of the data, which is pretty good, right? And if we got one dependent variable, it's pretty straightforward. And remember this XKZ comic where R squared is 0.06, so this line is only explaining 6% of the variation, so it's like, that's very useful. Of course, in real world, we usually don't, we've got more independent variables than one. So again, I just created a fake example. I've got two independent variables. There's my function. And what I do again is I just add some random noise to it to make it slightly more realistic. Another problem is when you plot 2Ds, it's a 3D, you should do a 3D plot, right? And so we're projecting it down, so we're not explaining the entire variance because it depends on both X and Z, right? This looks a little better, but again, we're not getting the entire picture because it's a 3D image, right? We're projecting it down into two different axes. And so fitting the model again is the same thing we do. And now when we look at the coefficient, we get the two coefficients, right? We get the intercepts. Now we can, actually compute the function if we want, right? Here's our actual model. And the actual was, 2x, so it's 1 point, so it's not quite as accurate. And 3, so it's not quite as accurate as the, and then the intercept is further off. Looking at the residuals, the mean is pretty close to 0, but the sum is not. Look at the residuals, again, taking 3D image and squashing it down to and of course, the more data points we get, the closer it gets to And the thing you have to be careful of is, right, the R squared value is going to be larger the more independent variables you have. Doesn't necessarily mean that it's more accurate.
Is there a way to do like an explicit R squared?
Yeah, I don't know. There should be, but I don't know. Yeah, I hope so, but. So it was linear regression. So Scikit Learn, Bayes. Okay, just install this. So we also saw an example with linear regression, right? And the process is pretty simple. Figure which model you want to use. There's various parameters that you have to choose. Range of data so that independent variables are in a matrix, and a target vector. Then you fit the model, and then you can apply the data to other data, either your actual data or data you set aside to verify your model. And that feature matrix needs to be two-dimensional. So as solving linear regression, we had to, right? Same example, right? So X is just an array of elements, Y is an array of elements. The capital X becomes an array of arrays. And then when we fit the data, right? Again, we need to make sure that independent variables are two-dimensional. And then I did look at the actual values. Then I knew what the model actually was, and then look at theirs, and it's pretty close, right? So that is the same process whether you're doing linear regression, random forest trees is just pretty much the same. There's a common technique, Bayes, and it's the idea behind Bayes is very, very simple, and it's surprising what you can do with a simple idea. And so here's a simple example to illustrate it. So we have 20 teachers, 12 are male, 8 are female. We've got 80 students, 48 are male, 32 are students. And then the standard notation, P of A is a probability of A, right? And then again, standard notation, P of A slash B is a probability of A given that we know B is true, right? And then the reverse is probability of B given that A is true. And then Bayes' theorem basically says the probability of A given B is equal to the probability of B given A times the probability of A divided by probability of B. So we can look at what's the probability that of a teacher given that we know someone's male of this population. Well, the probability using theorem, the probability of given some of the teacher that they're male. Well, if they're a teacher given a male, the probability is 12 over 20. Probability of their teacher is, well, there's 20 teachers out of the population of 100, and the probability of being male, there's 60 out of 100, right? So then we can use Bayes' theorem. The probability that there's someone the teacher given their male is the probability of the male given their teacher times the probability of teacher divided by the probability of male, and then we can now do simple arithmetic, right? And we just do the computation, and we get 12 out of 60, and yep, there's 60 males and 12 more teachers, right? So it's useful when, we may know probability of B given A, but we don't know the probability of A given B, right? And it's surprising what we can do with this. And notice we haven't made any assumptions about hardly anything, right? There's no distribution. We've assumed there's no distribution assumption at all. It's just basically simple probabilities. So let's use it to do some classification. And the idea is you divide things into groups, right? And this can be a wide ranging of things. So it could be, well, you got blood tests, and you want to know, do these people they've got the SID-19 virus or not, right? So look at the values, and there's maybe certain, numerical values which measure various things, and now we'll look at people who don't have and do have, and look at these numbers, and there's going to be a range of things, and so now we've got, I want to classify, they have it or they don't, right? It could be looking at restaurant reviews. Is it a positive review or a negative review, right? So using Bayes' theorem, right? Given we have a certain set of features, we want to know what's the proper label, right? Do they have the virus or not? But to do that, we just need to know, given the fact that we have this particular label, what's the probability of these features occurring? Which is different, right? That's something we can sample a population and figure that out, right? That's a slightly different thing, right? Probability label, again, we can again sample a population and figure out how many people have the virus, how many people don't have the virus, and the probability of those features being true, right? And so yeah, there's Gaussian naive Bayes. And here we're assuming the population is Gaussian or normal. So some data. Make blobs is just a Scikit Learn function to generate clusters, right? How many items? How many clusters do we want? Various parameters of how far we want the cluster. And then you want to plot it. And so scatter plot, we're getting, again, when we get this, the standard notation they use is capital X is the feature, right? So it's already two-dimensional. So we're looking at only two clusters, right? So we're plotting two parameters, and there's the coordinates. And here we're saying is we want to color the map based upon the y values, and the y values is cluster 1 or cluster 2, and then that's the colors we want to use. All right, so here are the two sets of clusters that we have. And so it's pretty clear the two clusters, although this area is getting pretty close, and then where do we draw the line between the two clusters, right? And so yeah, various values, right? They're thinking y is just either 0 or 1 depending on which cluster it's in, and x is just the coordinates for each point. And so this is the crazy make blobs, various parameters you can use. And then the scatter plot has various features. I spent a lot of time tracking down just the documentation, and I should have assignment 2 out tomorrow, and then you'll be spending lots of time looking at documentation. So again, the process Scikit Learn is pretty straightforward. I've generated the data I want to use, and so I create the model. I want a Gaussian, I have Bayes, and now I fit the data. Create a random generator, and I just create a bunch of different points, right? So I'm just creating some 2,000 random numbers, right, in pairs, and then I'm multiplying it times this and adding this to get the right area. Right, so this is an example of that gives me a bunch of pairs. I can multiply it and I get values like this. My new xn just becomes, again, it's a two-dimensional set of points. And my x values are between -6 and 8, and the y values are and once I've got that data, I can now predict, give me the new values, predicted values. Now I can plot them, and we get divisional plots of dark, and then the predicted values, what cluster it be, right? So the light blue, right? So it's basically a sort of line here. That's everything below it is going to be in one cluster, and above it in the other cluster. And we can use this to classify all kinds of things, right?
What model we exactly use for model prediction? Is
What
there a default one or?
we're using this model, yeah, the Gaussian model, right? Which points out that saying model is not very informative, right? It would have been better to say at least Gaussian NB model. Then we know we don't have to ask what model it was. Right, so it's so far so good. So it's fast. And pretty easy to understand what it's doing. And the nice thing is there's not many parameters to tweak, so you can't overfit. Although once you start doing more complicated things, it can take some time. So yesterday, someone from the biology department contacted me and said, "Oh, a graduate student is running this Gaussian model, and it's taking 3 weeks to run on, and that's not the full data set yet. What can we do to speed it up?" It's like, what are you doing? But they're using iterative model, so it's iterating for. Yeah, right. So it's various times when this makes sense to use the naive phase. So we can, like I said, we could use it to predict whether a review of a restaurant is positive or negative. But then we need to divide text into clusters, right? And how can we do that? So we have to convert text to something else that's right. And so just a simple example, right? So we've got just 5 words, right? One thing we do is we can convert sentences into vectors. We basically say, okay, there's our 5 words, so we're going to have a 5-dimensional space, and that's dimension 1, 2, 3, 4, and 5, right? So okay, we've got 1 word in dimension 2, and so there it is, and then at that's not right, because it should be 1, 2, and then dog, right? So that should be a 1. And then we knock twice, and so that becomes a 2. Well, but sad's not in our space, and so it doesn't count, right? So one way is, right, we just take all the strings and tokenize it. And then count the occurrence of each token. That becomes a vector. And then there's a problem of some words don't really provide any context. It occurs everywhere, and so if it occurs everywhere, it's not helping us decide between. So all the common words we just want to throw out, right? So either just throw them out or weight them differently so that. Also, the other problem is, should the word string be different than strings? Right? Right. So often you would then want to normalize each word to some sort of base. And people have produced a dictionary of, here's how this token should map to here because it's the base word. And so now we can go through, and if we want to view restaurant reviews, we can basically go through, and either you have your undergraduate students or your graduate students do this, and we're just going through and reading all the reviews and just positive or negative, right? But you need someone to, if you train the model, we need to know the truth, right? Is it positive, negative, right? We can, drop all the important words, convert this to
How would you
Oh, isn't that fun? Well, extreme negative and extreme positive, right? I hate this place. The service is terrible. The food is awful. Blah blah blah. Best place I've ever been in, right? And well, we were there. It's okay. Right. And that becomes a problem, right? Because extremes often are. But then, we can start. And so then what you do is, the professor goes through and looks at a few, and then these are positive, these are negative, and train the graduate students and tell them to come to us. And they then do some, and then they tell the undergraduate students that, okay, here's it, right? There's a problem. So a few years ago, this gaming company wanted to use machine learning to do two things, right? They take your cell phone and you have a Sudoku puzzle, right? Where you have to put the numbers 1 through n and then write 1 through 9 in the right place, so they all add up to, each row and column will have one. And they want to do two things. One is you take your cell phone and you then, basically turn the camera on, and it will recognize all the characters, and then it will solve the puzzle for you. So it required two things. One is recognizing the numbers, right? And the problem was you've got all the square boxes and the numbers, and so what they do, they went out to the bookstore and they bought every Sudoku book they could find, and they cut all the puzzles up, right? And then they basically scanned them all in, but then they had to someone tell me that's a 2, that's a 3, right? And so they put it online, and then people, just go through, and then some people, they had to then double check, and they had someone else go and check, because some people were just like, oh, I'll just put down the random value. And it may be, but it's not big enough to worry about.
Yeah, I'm just wondering, if there's actually a way
I actually played with building a Zuko solver, and it doesn't take. You can restrict the space fairly quickly because again you can't have the same number appear in a column or row, and so they start off with various spots. So it greatly reduces the space you need to look through. So the number of combinations is not too bad. And their main problem was, as soon as they put the application out, no one had a Sudoku puzzle in hard copy, so they did it on their screen. And the machine learning algorithm was trained on hard copy and not the screen, and it couldn't recognize the characters. So the programmer spent some long nights retraining the model. But again, it's just, going through that hard work is you have to go and have the ground truth. This is positive, this is a negative review, and you have to figure out what that means. Right, so we can basically drop all, rate them as positive, negative, drop all important words, convert the words to zero punctuation, do various things like that, and then create a vector of all remaining words and convert each review into a vector. And then it just becomes, you have your independent variables, the vector, and then you've got the ground, is it positive, negative, or not? And then we're back to the same situation we were before, right? That's it, right? That does lead to some interesting problems. One is you've got 100,000 distinct words, and you've got your vectors 100,000 dimensions. So things get pretty sparse. And so there's several things to do. Is we're going to use a sparse representation. So instead of having each vector being 100,000 units long, we can just represent, well, if we only have 40 values in it, we store the value and location it's going to be in, right? So it's a much denser and so, people have done this all the time, right? So Scikit Learn has different ways of doing this, right? So there's a count vectorizer, which take a text document and produce the token. And so there's different vectors, so we can do birth normalization, and we can tokenize, we remove these words which don't have any meaning, we drop punctuation. Last I checked, which originally wasn't good at converting words to roots, vectorize them. Term frequency, so there's different things we can do, right? So the raw count is the frequency, term frequency per document, right? Either true or false. You can also do the frequency divided by the number of words to normalize it. And then finally, we take the log scale. Basically, a transformation people find useful in normalizing words. And the IDF is inverse document frequency, and it's basically if the word's everywhere, then it doesn't provide information, so don't count it, right? And then the TF value is you basically combine the two so that when you get value becomes high when it occurs a lot in a document or it doesn't occur in very many documents. And the more common the word is across all documents, that value goes to 0. And to use a very count vectorizer, probably the same process, right? We get the model, here's our data, and we then transform it. And then it basically is divided the corpus into individual words. And it converts each one of these into a vector for us. Just by doing the count, right? So the first one is, well, 1, 2, 3, 4. So this is the last one, is the middle, the is, right, first from the end, right? So we start finding the document, and then first, and is, right? So we can use this to convert each one into a vector, and now we can start use that as a and then we can, given that model, we can now take a new document and convert it into so now we can basically have you cheap labor go through and label all your views as positive, negative, right? And then use a count vector and then see how well that will take a new review and determine whether it's a positive or negative or neutral review. Yeah, there's various things we can do, which, again, it's looking at the documentation to figure out what feature you want to use. Using this vectorizer, again, the process is, it's like identical, right? It's like, I came across a couple weeks ago an article by a data scientist who said, data science is being commoditized. He said, well, he got his PhD, he did all this work, and analyzing this and this and this, and created new techniques, and it's like, it was his PhD thesis, right? It took him, it takes months or years to get this done, and now it's like, there's this library to do it. Okay? He said that's what's happening is, right, as soon as someone comes up with a new idea, a new technique, right, and it's, someone gets a PhD, and they spent 2 years of their life making this, and then 3 years later, it's like, okay, it's in 3 or 4 libraries, and it does the same thing, and maybe even better than he did, but that's life, right? So again, the same corpus, same process, we transform it, and then we can look at the weight each document, each word is going to give. Again, we now do the same process, right? We can now take these are basically vectors, right, for each document. Once we classify them, we see if they create clusters, and then use them to predict things. Another way is looking at n-grams. A sequence of words, right, that occur in order. Right, so fetching news groups, look at their name, right, various news groups fetched. And then various articles. Right, so we pick these particular groups to as a training set. And we pick another subset to be our test subset. We get various descriptions, right? And so now we're going to see, given a particular message, can we figure out which, what group it belongs to? We get 2,000 articles. Right, if we look at various data sets of what categories belong into, which group it belongs to. And again, the process is pretty similar, so I'm going to create a pipeline so we can do the same thing. And so we're going to do a series of transformations. In the end, we want something to create an a fit function. And now I can train the model, and now I can use it to predict, right? So pretty much these, whether you're on Scikit-Learn or Spark or in R, most of the standard algorithms are implemented for you, and there's a pretty straightforward way of applying it. Right. In this case, we'll just pretend which group it came from, but news group it would belong to, but it mapped each group into a number. And we can ask then, give them the label 1, which news group was that? And we can and look at various art postings and appreciated in. This is a sample. I was talking about fonts, right? An ATM, Adobe, and we were looking at religion, space, and graphics. It's pretty clear someone talking about fonts and ATM is in the graphics group. And predicted so. So the goal is basically to understand what these things do so you can pick the right model, but then the process is pretty similar. And ideally one would take the machine learning course we're taking in this class, so then I have to talk about this. And that's going to happen in the future. When this course, machine learning course, gets a regular course number, the problem is you cannot require a 596 or a 696 for another course because that's a temporary number. So I think we probably don't want to start looking at clustering. So we'll start looking at clustering on Thursday.
I have a question, and it's not related to big data.
Okay.
So I'm asking this on my friend's behalf. So he's saying that he actually interviewed for a company, Qualcomm, recently.
Yeah.
And he said that they're interested to know if he gets offered the position. It's a full-time role. So can he get a CPT like from maybe next week or something, while being currently enrolled as a student over here?
Okay, so there's two parts to that question, right?
Okay.
One is he allowed to work full-time during the semester?
Sorry, what's that?
One is he allowed to work full-time?
Oh, okay, yeah.
And that is, so the answer to that question is if his GPA is 3.2 or greater, then we do allow international students to work full-time during the school semester.
Okay.
The second part is, can he enroll in the CPT course now?
Right.
And he should be able to. They do accept late ads for that course, although at some point as we close to the end of the semester they stop accepting it because it's too late.
Oh, okay.
But he should be able to do.
If it's like from next week or something.
Yeah.
And I'm pretty sure his GPA is above 3.5 or something.
Yeah, that is.
Oh, yeah, and he's also enrolled in just 2 courses. So like he just has 2 courses this last semester, and
well, basically my feeling is you're a graduate student, and you should realize that there's 24 hours in a day, and
Right. Yeah.
if you overcommit yourself, and you suffer the consequences.
Yeah. That's true. That's true.
Right. And
Yeah, but I'll let him know the higher details, like of what you told me.
yeah.
And because I think his company was, the HR of his company was asking him, because like if we ask you to join maybe next month, so would you be able to do that? So that's why he asked me.
Sure. Yeah. So the answer is the GPA is high enough, and he enrolls in the CPT course soon. Then
Yeah, just soon. Just make sure it's soon, right?
Right. Yeah. I mean, if it's last week of April is probably guaranteed that they won't allow you because you're almost at the end of the semester.
Right.
Now it should be fine.
Okay. So March should be fine.
Yeah. I'm not sure when the cutoff comes, but
Right. Yeah, I'll let him know.
yeah.
Thank you so much.
Right. Oh, I've only taken 2. Oh.
What's that?
Oh.
Oh, what happened?
If he's taking 2 courses,
Yeah, he is.
it's
For
gonna,
6 units.
yeah, he'll have to pay a late fee plus the extra tuition.
Oh, really? So,
When you take 2 courses,
Uh-huh.
right, you're only taking 6 units,
yes.
and so then as an international student, you pay the regular fees plus the out-of-state fees.
Mm-hmm.
The out-of-state fees is just for that 1 unit,
Oh, yeah.
but the regular fees, if he's only paying for 6 units, and now he takes a 1 unit course, now he's taking 7 units,
Mm-hmm.
so now he has to pay for 9 units.
Oh, so $3,000 more? Something like that?
I don't know if it's 3,000, but I forget what it is, but it's going to be,
But whatever it is for just, it's going to be for 9 units.
right, he has to pay for
9.
9 units in-state, and then for 7, he has to pay for that 1 extra unit for the out-of-state, yeah.
Oh,